Good morning. Today we are going to discuss triboelectric effect and try to do some demonstration through this online lecture. So I chose a demonstration that you could do yourself while watching the lecture. And I do that and show you in the next two slides. So I encourage you to actually do this demonstration. If you have the resources, which is nothing but just a tape. So let's see what that is. The first experiment. Okay, let's try this experiment. We're going to take two pieces of tape. Stick them, make sure they're stuck really well, and then another one. Do the same thing. And then we're going to peel them off. And you can see they're rappelling. As I take one tape, I can move the other tape. So there is some phenomena going on here that you can see. And let's do another experiment now. Okay, so now let's look at the next thing. Okay, let's try this experiment. We're going to take two pieces of tape. Stick them, make sure they're stuck really well, and then another one. Do the same thing. We're going to do another experiment now. Now what we're going to do is we're going to stick these tapes on top of each other instead of putting them on different places. So I'm going to stick one here, and then I'm going to stick another. Make sure they're stuck properly. And now I'm sort of going to make some handles here so that I can handle these two tapes. So I'm just going to handle here. Okay, so now I peel them off together, and then I'm going to peel them off here. You can see the electrostatic attraction. Right? I encourage you to do this experiment yourself. Okay, sorry, I played the first video twice there. But what you are seeing there is the triboelectric effect. That is, for example, it's known that if you take a silk cloth and rub it against a glass rod, there is some exchange of charge. Here in the example, what you have seen is, for example, if this is the desk and you have a piece of tape here, when you peel this tape off, there are functional groups, these organic functional groups within the polymers that make up the tape. Those get ionized, those get charged because some bonds break, and because of that, you see that they're differently charged when you stick them separately in the first experiment, and then you stick them on top of each other in later experiment. I encourage you to use this experiment to validate Coulomb's law, which is Q1 Q2 by R square, as we started discussing. But before we got into the details of electric field, I wanted to mention triboelectric effect because this is one of the first effects that was observed to know about this new property that massive bodies can have, that is charge. So when we are saying charge, it is a charged massive body, and so when two things undergo friction, they were able to, separate charge out. And from here, we could know that the charge behaves in two different ways, like you have seen in the examples. Unlike gravity, now we have two different types of result. That is, they can either attract or repel each other, and you could do this even by rubbing a balloon on your hair and trying to attract pieces of paper. And the static electricity, that the static that you get, is also from residual charges. But here what I want to show you is how we can take this triboelectric effect and convert that into devices. So one of the things that we did in our lab to take advantage of this is we coated just normal plastic that's there in water bottles. So this PET is there in wastewater bottles. So we take PET from wastewater bottles and then coat it with a very nanometer thick layer of indium tin oxide. So ITO means indium tin oxide, and that's a conductive coating, and it keeps things transparent. So it's used in these transparent touch screens a lot. And we coat it to nano size because when you divide a surface, uh, it's nanoscopically rough, then there is more triboelectricity because there is more friction when you are rougher. And then at the bottom we have a polyimide. It's a polyimide tape. Its commercial name is Captain. And then we stick them together, and using this, essentially when the top electrode and the bottom electrode are rubbed together, they separate into charges because of triboelectric effect. And so when you take them apart, when you push them apart, you can get an voltage signal like this, and you can get a current flowing in the circuit, right? And so when you press and release, you get these up and down, because the current is going either this way or that way, depending upon whether you're pressing these surfaces together or away from each other. And this you can convert into real devices. For example, here, you see my student. He developed a triboelectric nano generator that was able to light up, that was able to power up things like 200 LEDs. So here is an example video. So this is a triboelectric nano generator. What you see here, that is the same thing as what I have shown you. Just a PET layer coated with ITO and some Kapton tape. That's it. There is nothing, no batteries, nothing. And this is connected to LEDs, and these are the LEDs. There is no battery here. So as the student steps on it, you see that the LEDs are glowing because the mechanical energy that is pushing these two layers together is leading to triboelectrification, which is leading to a flow of current, and that's how the lights are able to glow. So you are able to take mechanical energy and convert it into electrical energy for these triboelectric nano generators. So you can see a more controlled one here. So here is a more controlled push. Again, there are no batteries. This generator is directly connected to an oscilloscope, and an oscilloscope is used to measure how much voltage is coming out in this case. So if you see, as the piston goes up and down, you will be able to see the voltage spikes. Okay? So that's coming from triboelectrification. So as this is pressing up and down, there is an voltage spike that is released. So that's how you're generating, you're converting mechanical energy through triboelectrification into electricity. So this can even power a calculator. For example, we made a calculator which you could just do using mechanical power to electrical power in between, then instead of having a direct capacitor or a battery in the calculator. And this could, even if vehicles go over it, you see the signal. And here is, you can integrate this into textiles. So as a person is moving, that motion generates triboelectrification, which can be harvested into usable electricity there. And so people who are interested in the scientific specifics, you should learn how to do journal search. So I think this is a good place for that. So you can pull up our paper. You can see how to look this journal up, how to download that paper, and this should come to you for free of cost from Clemson Library. So and then read about it and learn more about it. And then we also did wireless. So this you could have so much triboelectrification that this triboelectrification essentially what it does is as you apply the mechanical force, the charges are getting separated, and if the charge separation, if the separated charge is huge, as we have seen, it can produce a lot of voltage. And as we have seen, if I have a charge, because for example, if I have a charge here, the flux spreads out as surface area. That's why we have 1 over r squared dependence. So if I produce triboelectrification at this point, the voltage of that will fall off rapidly as I go away from it. But if I'm able to produce a lot of triboelectric charge, then I should be able to produce enough voltage that can be spread over several meters, and that's what you see here. So here is another type of triboelectric nanogenerator. We designed a nanoscopic grid with graphene, and we 3D printed that grid. And from there, we made this wireless triboelectric nanogenerator. Again, there are no batteries, nothing. The oscilloscope is reacting to what electric field this generator is producing, and here is an electrochromic screen. So if the voltage is at a certain level, the electrochromic screen basically becomes transparent, and so that's what you can see here in this operation. So it's sort of a wireless triboelectric nanogenerator, because that tap is producing so much electricity, so much charge that you're able to sense it here in the oscilloscope. So the distance between this and this, I think, is around 7 meters, or sorry, 3 meters maybe. So it is able to produce so much charge, triboelectrification, and you can see this really in devices that you can make and use. And the reason I'm showing you this is based on the tape experiment and experiments like this. It's not so difficult to imagine how the planar, how the field is going into the planar. So you can see that as the student hits this, there is charge, but you're able to feel it here because this charge is disturbing the planar around it, and that is basically propagating out to where the place is. And because this propagation dies out of as the surface area, if the source is strong enough, then it can definitely have an effect here. And that's what is happening here because of the design of this instrument at the nanoscopic level with the right materials. It's able to produce enough voltage that can affect the an electrochromic screen, which is very far away, without having any batteries or without having to rely on any power, external power. So that's one thing that I wanted to share with you. And so you can even see that here, another example of the wireless system. That's my student who did that. And so again, there are no batteries. Whatever power connection are essentially for powering the oscilloscope itself, but there are no batteries here. So let me show you this one. So you can have a capacitor or a battery, and as you are applying mechanical energy on this, it's producing enough voltage, and we showed that can wirelessly charge a capacitor, because now there's voltage difference between these two ends of the circuit. So the capacitor gets charged, and in fact we were able to experimentally charge a capacitor, 1 microfarad capacitor, in a minute by staying 7 meters away without any connection. So